so now that we've talked a little bit about the sample distribution, let's talk a little bit more about the central limit theorem as well as how to calculate standard error, because we are going to use standard error in order to calculate our new z-scores for this particular section, our chapter. So the central limit theorem says that for any population with a mean of mu and a standard deviation of theta, the distribution of the sample means for a sample size n will have a mean of mu. Now, what that means is that your population mean and the mean of all of your samples, so that means I take 100 samples of size n and I average all of those together. That mean and the mean of your population should be the same value. Okay, so in your homework you'll see that the mu equals the mu m, or the mu sub n. That they're just saying that the means are going to be the same. Now the standard deviation is going to be different. It is going to be your standard deviation divided by the square root of your sample size. And it will approach a normal distribution as n approaches infinity. So what that means is the larger my n, the closer my sample distribution becomes normal. Gets that nice bell-shaped curve that we were talking about in the previous video. So the distribution of sample means is perfectly normal if one of two things happens. The population from which the samples are selected is normal. So if you had a normal population to begin with, then the distribution of your sample means is expected to be normal, no matter what your n is. Okay. The other thing that could make your sample distribution normal is the size of your n, the number of scores in each sample. The number of participants in each sample is relatively large. 30 or more is what we tend to say. So if we have sample sizes of 30 or more, when we get all of those samples and average them together, then that graph should be fairly normal. So the expected value of m, the mean of the distribution of samples, is the same as the mean of the population. Again, I'm just reiterating that for you again, that my mean of my distribution of samples and the mean of my population should always be considered to be the same value. All right, standard error. So again, remember that's our standard deviation of our sample means. So standard error, same thing as standard deviation of the sample means. So we use a theta with a little m. So the little m is telling me that's my sample means. And I do my standard deviation of my population divided by the square root of my n. So what this does is it provides a measure of how much difference is expected from one sample to the next. Remember, standard deviation is all about the variance or the spread of the data. So when we talk about the standard error or the standard deviation of the sample means, we're talking about the distance between the means of each of these different samples. A small standard error indicates that the samples are fairly close together, just like a small standard deviation means that the scores are close together, they're grouped together. A larger standard deviation, or larger standard error, indicates that the sample means are more spread out over a larger range. Remember, this is all, standard deviation is all about variance, and the smaller my standard deviation, the less variance I have in my data, the less spread out my data is. So standard error measures how an individual sample represents in the entire distribution. So it provides a measure of how much distance is reasonable to be expected between a sample mean and the overall mean of the distribution. Again, we're talking about the average of all of the samples versus one singular sample. That's what we're talking about when we talk about sample distribution. We're talking about all of the samples we could possibly have, what is their mean, and then we are comparing that to one specific sample. So let's talk about calculating a standard error, and we're gonna change our n value as we go through this. So the first n we're going to start off with is 1. So we're taking samples that only have one participant in them. And notice that our population standard deviation is going to be 5. We're going to use that 5 throughout this whole problem. So to find our standard error in the first one, we're going to do 5 divided by the square root of 1. Well, the square root of 1 is still 1, so 5 divided by 1 gives us 5. Notice it didn't change any. All right, so let's do it for n equal to 5. So now we're going to do 5 divided by the square root of 5. When we do that division, we get 2.34. Notice that I have a larger n and my standard error has decreased. Okay, remember we talked about the larger your n, the less variation you're going to have in your means. So the standard deviation should be dropping as we go through our larger n's. So let's say we had an n of 20. So now we have 5 divided by the square root of 20, which is going to give us 1.12. Again, noticing that that is quite a bit smaller than the previous one. And let's do a big one here at 100. So we have 5 divided by the square root of 100, which is going to give us 0.5. Again, what I want you to notice is as my sample size increases, the size of the standard error decreases. So larger sample sizes tend to be more accurate. The other thing I want you to notice is that when I have a single sample, so I got my n is 1, single score, my standard error and my standard deviation are actually the same exact value. Okay, so I hope that helped kind of explain standard error a little bit. If you have any questions, please let me know. And in the next video, we're going to talk about z-scores using our standard error.